So, welcome everyone. My name is Rohan. I'm one of the senior research engineers at Sovereign. I work with Chen. And yeah, welcome to the workshop. So, a little bit about the agenda. I'll spend a little bit of time talking about Sovereign and some general stuff that a lot of people might be familiar with, but it's still worth reiterating. We'll go through like the bulk of the demo would be actually be building like a very simple module using the Sovereign SDK. And after that, we'll also cover other aspects of the SDK that I'm not able to cover in the demo because, it's relatively time bound. And then we'll spend a little bit of time talking about some of the current and future work that we're looking at. So, yeah, Sovereign's mission, if I had to summarize it in like the most succinct way possible, it's to make it as simple as possible for developers to build powerful blockchain-based applications. So what does it mean, right? Like when we say simple, it's both in terms of effort and time. We want to be able to make it easier for developers to build. And by powerful, sure, you can deploy a smart contract anywhere, you can deploy applications in several places, but we want to give developers as much flexibility and their applications to be as powerful as possible. So let's look at what the problem statement is, right? Yeah, building blockchain applications is hard. Like most of us here know it. And what are some of the common approaches? So you can deploy your application as a smart contract on a layer one. But what are the problems with that? There's no dedicated throughput. Your state transition function is rigid. That means the abstract state transition function is already coded into the layer one, and you can't really change or customize consensus or anything if you want to. And there's also a problem with value accrual because most of the value is accrued to the infra layer or the layer one and not your application. So that's the issue with smart contract rollups. You have application chains. They do solve some of the problems above, but there are new problems now. So you need to spend developer resources on non-application logic because now if you have to build your own app chain, you need to look at blockchain logic. There are some SDKs, but you still have to consider networking, consensus, storage. These are all choices you need to make. And you also need to recruit a validator set. That's like a very prominent problem because now you still have to be decentralized. You need to satisfy Byzantine fault tolerance, and your coefficient needs to be high enough to prevent any sort of reorg attacks. So standard problems. So what about rollups? Yeah, they solve some of the above problems. They eliminate the need to recruit a validator set because now you're using the underlying DA layer. You have dedicated throughput, something that your smart contract chains don't have because now all the resources you have resources for your application. The value accrues to the application, which is pretty great because you're capturing all the value and not some other layer one. And the STF is customizable, so that is like beneficial, like similar to application chains. You have full control over the logic that you encode around the state transition function. But this is the core of the problem, right? Even building rollups is actually hard. It solves a lot of the problems, but the effort involved in building a rollup is not trivial. Like you have to make a choice about the proof system. Like, okay, am I going to be an optimistic rollup, or am I going to, how is my finality determined? How are nodes going to consider something final? Like, is it optimistic, or are they going to wait for proofs? And the second problem is censorship resistance. So now, this is a commonly brought up problem that your application rollup can censor, or they can prevent users from interacting with the chain. So that's one other problem. And then obviously, even in a rollup, there is slightly less protocol engineering, but you do need to write code that interacts with the DA layer or whatever layer one that you're using. And that includes like things like RPCs, your goal as an application developer is to build the application, but now you're doing all of these things, like you're writing code to submit blocks to the DA layer, consume them, and then build like an RPC server to let other people interact with it. And by tooling, I mean even like wallets and everything. Like there's a lot of additional stuff you're doing as an application developer. And there's protocol development. Like I made it separate because even if you use an SDK, you still need to debug networking issues, and like for testing, you need to be able to launch multiple machines. So there is a lot of work that you're doing. So the direct consequence of this is that there are very few feature complete rollups. Like I think if you went by the actual definition of a rollup inheriting security from the underlying layer, there's just one that actually does that. Everyone else probably makes like some compromises, usually because they're like, okay, we'll decentralize later, or we'll add in fraud proofs later, or only this specific address can submit fraud proofs there. So there are trade-offs like that, right? So this is basically where Sovereign SDK comes in. The goal is to address each of these problems. So what is Sovereign SDK? It's a free and open source toolkit that you can use to build rollups. So Sovereign lets you seamlessly plug in either an optimistic or a ZK proof system. So by seamless, we make use of, like Sovereign is built in Rust, and a lot of it is actually, we provide abstractions around having like the right traits that a developer needs to implement. So you have a lot of scaffolding and boilerplate already built in and auto-generated. So the end result is you can seamlessly change the proof system. You don't particularly need to give too much thought to it. Not even just ZK, but even multiple types of ZK proving systems. And then censorship resistance, yeah, we have a single sequencer, but we also support base sequencing. So those other kinds of sequencing algorithms are also pluggable. And the code to interface with the DA layer, there are already some built-in adapters that we already provide, Celestia and Avail, and there are more DA adapters that are in development. And we also auto-generate a lot of the tooling and other infra that you need. And even the protocol development part, which is, like I mentioned, like the storage is abstracted, the networking is abstracted. Typically when you have a chain, you also, what happens when a new node joins, right? It has to start syncing and catch up. There's like config management. So all of these are handled by Sovereign SDK. And how to use it? Yeah, like you focus purely on the application logic, and the rest of it is mostly like plug and play. Like you can plug in existing DA adapters. You can also customize them if you really want to. It's the same for prover systems. And for the SDK, once you implement the necessary traits, the SDK auto-generates like the RPC for you. We're also working on generating an open API specification so you can have any client, like lots of languages have tools to auto-generate a client if you have an open API spec. So the CLI tooling and then the prover, and you also get the node implementation, which is the full node and the light node. You don't really need to particularly care about, the ultimate goal is that you focus purely on the application logic, whereas, and if you implement the right set of traits, or you plug in adapters that are already implemented, that does the job for you. And one of the reasons we use Rust is, it's performant, and the type system is actually pretty expressive. So we try to encode as much as possible into the type system so that when you're running something, it fails at compile time rather than, hey, you plug in this protobuf or something, you start running, and then the only way you know something is wrong is when you actually send a message and it breaks in production, right? So yeah, that being said, we can probably step into the demo, which is like a simple coin module. It's a live coding. I'll try to live code it, but I do have the changes on a branch in case we start seeing like weird compilation errors or something. I hope the font is readable for everyone. Okay, yeah. So a small overview of the repository itself. There's a folder called examples, and this is actually one of the best places to start if you really want to look at Sovereign, like get into Sovereign. There's like a demo rollup and a demo prover, and we'll mostly be in the demo rollup area. But yeah, if you want to create a new module or a new, like in our case, it's a coin module, right? So it's typically the same as starting like a new crate or something. So if we go into, yeah, I'm calling it simple token. And at this point, it's just a standard Rust crate. There is nothing in it, just the test code. So I will import some dependencies. I'm mostly copy pasting a lot of this stuff because typing it will take like much longer. Uh, but if we look at what we imported, yeah, like it's just some standard serialization libraries and everything. But we're also importing like the module API and a few other things that are relevant to when you create a new module. So yeah, so what do you primarily need when you create a new module? So I have 3 files here, or you know, let's make it a little bigger. Yeah. So when you create a new module, you need to be able to submit transactions to it. You need to be able to read from it, which is, you know, like what is the state, what is the value of a certain like account or what, like you need to be able to query state, you need to be able to modify state. And there's genesis, which means when your module is first deployed, what is the initial state, right? So for each of these, we can create like 3 files. We'll call them like call.rs, genesis.rs, and query.rs. So those are the 3 files. And yeah, so before we even look into that, let's look at what the structure of our module is, right? So what we really want is, like, this is the core structure when you create a new module. It's like creating a new contract, essentially. So let's look at what I did here. I'm auto-deriving module, which is like part of the documentation, you can see that. But ultimately, I'm creating a struct and I'm annotating a few things. I'm saying that, okay, there is an address for the module itself, which is mandatory. If you don't do that, you get a compilation error. And there are 2 pieces of state. One of them is the supply, which is U64 value. The other one is balances, which if you're familiar with Ethereum, it's literally just a hash map that stores an address to the balance. So this is a very simplified version of the module because for the purpose of demo, just to understand the core aspects of it, right? And then you have the standard imports that I just want to add here. And there is something called like the config, which I can explain in a little bit. It's basically, this is what determines what the initial supply is. So yeah, you created your struct, which represents your state. But after this, now you actually need to implement the module trait. As I mentioned, like a lot of Sovereign is actually implementing traits that are defined in the SDK because the rest of the engine or the runner makes use of these traits to run. So as long as you satisfy the constraints of a certain trait, you're fine. Like you can write anything that satisfies those trait bounds. So yeah, so if I do this, I'm just looking at why autocomplete isn't showing up. 1 second. Yeah. So basically, if I try to do a cargo check or something at this point, it will say that some of these traits, oh yeah. So I need to, one of the things you need to do is like all of it is based on like a workspace. So I do need to add it into the main, yeah. So we created a new module, so I'll just add it into the workspace here. So this is the simple token module. Yeah, so now it should be able to tell me if something is broken. Yeah, so it basically highlights the error saying that, hey, you are saying that you want to implement the module trait, but you're missing a whole bunch of things, right? So let's just say implement members and all the mandatory members. For now, we can just leave this as unimplemented, which is pretty cool with Rust. You can add that in later as long as it type checks. So for context, we already have a value C. I'll just use that. The config represents the initial state, and we just created a struct here that says, what do I need in order to initialize my Genesis state? I just need a supply of the token, and I need an address of the token. Naturally, you can make this more complicated and say that I also want to have a name for the token, or whatever those fields are, as long as they satisfy certain traits, it's fine. Like they need to be serializable because you're storing it in your RocksDB or whatever storage, right? So at this point, I'll just say, okay, my config type is actually this, and it's generic, so, and my call message. So the call message is, what's the call message that you're using for the transaction? At this point, I don't have, we didn't define the call message yet. So once we define this, we can just see if it type checks or not. It should, yeah, and it did, because that's actually one of the cool things about Rust. Even though you didn't implement it, you're not using it, so you can leave unimplemented for now, and as long as the types are correct, it's still okay. So yeah, so now that we have our basic struct, let's look at what the Genesis looks like, right? So in Genesis, what I'm doing is, let's see. Okay, so all we're doing here is we're implementing a trait for our, yeah. This is actually pretty simple as far as logic goes. I have my struct and I'm implementing like a function for it. This is just a private function. This is not really enforced by the trait or anything, but all I'm doing here is I'm saying, okay, I'm taking the config object, which is of the type that we defined, and I'm just setting the supply to whatever supply is part of the config, and I'm setting the balance of the creator to the supply. So just to explain this part, what's happening here is when I create my new token, the Genesis state will specify what the supply of simple token is. So I need to provide like a supply and the creator, the address of the creator. Those are the only two things that are needed for Genesis. And now in Genesis, we can actually write the specific code for calling that, which is, let's see. Yeah, all we're doing here in this place, and like the implementation for Genesis is basically just call init module, the function that we just defined here, with whatever config is passed into Genesis. So naturally, these variables are used now, so it'll complain. And yeah, for these things to be usable, you don't need to add them as like, this is a standard Rust thing. So mod Genesis, mod call, and mod query is not really needed, but I'll just add it anyway at this point. So let's see. Yeah, so this is the init module function that's being called when I actually, when the module is initialized. And if there are any issues, it will say Genesis failure, which is fine, because when you're starting up your new chain, you want it to break immediately if you misconfigure it, right? So let's get to the more interesting part now, which is how are we going to define what a transaction is for our call module, for our simple coin module, right? So the most basic thing you want to do, a more complicated module for tokens would have things like mint, burn, freeze, like there are a lot of additional features, but for purpose of simplicity, we're already fixing the supplier Genesis, so the only real call that we would need is actually just transfer. So this is kind of what it looks like. Let me just have this here. So what we have here is a call message. So this is an enum type, which is, if you're familiar with Rust, it's like the sum type. So what are the types of messages that my system can accept? So here it's just a transfer. And what does a transfer need to specify? Who am I transferring the tokens to? And how many tokens do I want to transfer, right? So that's basically the only message that is supported. But if you want to look at a more feature-complete implementation of this, in module implementations, Sovereign does provide like the bank module, which is, if you look at the call there, it'll have like a create token, transfer, and then a burn, there is like a mint functionality and a freeze functionality, as I mentioned. And this entire thing is an enum. So as long as you send the like the serialized enum to the application, it'll accept it. Like all of that is auto-generated. We'll see that in a little bit. But yeah, so now I need to actually encode what happens when I get a transfer message. So for that, you just need this function. Like you can write, this is the core of the business logic, right? What am I doing when I need to, like how do I transfer things? So we can look at the function. It's basically, you're getting the sender. So there's a context object that has information like who signed the transaction and everything, which is available to all modules. So you can get who the sender is and the signer is. So I have some very simple logic here without checked math or anything so that we can focus on the core part of it. So all I'm doing is I'm getting the sender, I'm getting the balance of the sender, I'm checking if what the sender wants to transfer. If it's less than the amount, I'm just going to bail with, okay, not enough funds. And then the rest of it is just some basic checked math. Like, okay, what's the balance of the person you're transferring to? I'll just increment that. That's it, actually. So in production implementation, you would have like checked math, if you're familiar with Solidity, which is like check add, check subtract, prevent overflows and things like that. But the core logic is still the same. If you're writing any module, this is where you put your, like you define what the type of message is, which is an enum. Different types of, different variants of the enum would be the actual messages that you want to pass to the system to update the state. And then you encode the logic on how to handle it. But these two are not connected yet. Like we have a call message and we just have a function, right? So how do I connect this to the actual module? So that's where this call comes in. So in Genesis, like when you implement a module, you need to tell Sovereign SDK requires you to specify Genesis and specify how to handle the call. So in Genesis, we wrote the logic. We're like, okay, there is a config that is always part of Genesis. Once it's passed in, you initialize the module with that. And for the call, this is actually quite, basically you need to, this is like the routing mechanism. When you get a message, you need to decide which function to call. So let me just see. Yeah. So this is all it really is. Like what you're doing here is, you're basically matching the message and you're deciding like, okay, what is my type? So here the call message. So this is one of the nice things about Rust as well, because you have type checking at this level. If you're trying to handle the wrong kind of, like an enum that doesn't exist or something, it'll just fail to compile right at the beginning. So I'm just saying that if the message that you got is a transfer message, then just call the transfer function by extracting these elements from the enum. So that's basically all that's actually happening here. So at this point we have, yeah, let me just quickly cargo check it and make sure it works or doesn't break. Yeah, so this happened because when we auto-filled the trait, it set call message to blank, right? But now we actually have an implementation for call message, so I'll just set it to that. So all of these are things that you need to specify. Oh, it's yeah, it's a generic. So now we specify what the context is, what the config is for the Genesis, and we're specifying what the call message type is. So at this point, it should type check without any issues, but yeah. So now we have, now what did we do? We filled out the Genesis. We filled out what kind of messages the system handles. So now we can also do like the query part of it, which is the RPC, like how do you read? So we looked at initialization, write. Now we're looking at read, which is also fairly, let me see, query? Yeah. So some standard imports that you need to use. And by the way, like I wanted to cover this later, but I can actually do it now. The thing is, I'm creating the module from scratch just to illustrate how it's done. But in the modules, there is like a module template that you can also use. which has like a very simple example with a lot of documentation around how like you can fill out all of these, right? And in like going a little bit, I think we're already currently working on like a cargo template, so you can just generate the scaffolding directly. So yeah, so let's get to the query. There are some imports, and yeah, this is the part where we're using macros to auto-generate a lot of this code. So what we're actually doing here is I just defined a response type, and for the response, all that the RPC requires is that it's serializable, right? So we have, okay, we're deriving some traits that Rust provides, which is serialize and deserialize. And then what we're doing is we're defining a simple function that says, okay, if somebody passes you an account, then query the balances. Like if you look at our original struct, it had these address, supply, and balances, right? So we're just querying balances and getting the account. So how does the actual RPC infrastructure come in? That's where these macros come in. So like Sovereign has a pretty rich set of macros where we auto-generate a lot of code. So if you say that you want to RPC generate, you just provide the namespace and what the name of the method is. And this is very similar to JSON RPC. Like there is a Rust crate called JSON RPC, which is how you define RPC servers. And we use the exact same annotation scheme. So all we're doing here is these are the two annotations that we added. This RPC is in the simple token namespace, and this function's name is getBalance. That's it. And all we're doing here is I'm querying the balance from RocksDB, and I'm returning the serializable struct. That's all the RPC macro cares about. And if you do something wrong here, it'll fail with a compilation error. Yeah, okay, this is fine. So at this point, our module is actually completed. Like we have the query, we have the genesis, and we have the library, right? So now how do you plug in this module into an existing rollup? Like you can, like I said, you can customize a lot of logic, including the state transition function and everything. But we do have a simple, like a demo rollup implementation. When you build your own rollup completely from scratch, there are a lot of things you might want to consider, like what is my address type? Is it 32 bytes, 20 bytes, or what is my signature scheme? Like, am I going to use SEC P256K1 or ED25519 or BLS? So all of those, there are pre-built adapters that you can just use. The demo rollup uses ED25519. It has like standard 32-byte addresses. It uses RocksDB for storage, and it uses Celestia for the DA layer. So all we're doing now is we're basically just saying, okay, I have a new module. I want to plug this module into my rollup, right? So what you actually need to do is there is the logic of your state transition function is defined in the runtime. So this runtime is basically just a struct that says what are the modules that are loaded. So demo rollup comes preloaded with the bank module, the election module, and a few others. So we just want to import our module here, and yeah. So to import it first, we have to just add it into this thing here. Let me just see if I have, yeah. So into the demo STF, I'm just saying, hey, I created a new module called simple token, and I just want to import it. So once I do that, I can add I can import the other things that I need here. So I'll just say, we called it like, 1 second. Do this. Yeah. So query and so these are auto-generated actually. So there's an RPC implementation and an RPC server. So if you notice, we didn't have to write anything related to RPC directly. So we're just saying like a simple token, and I'll just call it like a one second. you can actually see why it's complaining about it. Okay, yeah. This had to be like a public module, and I just made it like a private module, which is fine. It's a very simple fix. Yeah, just make them public. So now it shouldn't complain anymore. Okay, so now we have the RPC implementation and we need to plug in the module here, right? So let's put it right after accounts. We'll call it simple token, and that will be simple token, and it's not accounts, it's basically the simple token struct. You might notice there are a few places where we have like CFG feature experimental. So what we do is when we write new modules that are not, that we're actually experimenting on, we feature gate it with experimental so that, you know, people who are using it know that it's actually experimental. It's part of our release process. And you might also see like feature native. So the reason you have feature native is because there are certain things that you only need in your native code and certain things you don't need in the ZK prover system. So that's basically what distinguishes your non-ZK provable code from your native code. And it's fine, like most of this is abstracted, so you wouldn't need to directly delve into it unless you're modifying it. But yeah, so there is like the simple token here, and I will add it here as well. The thing is, this actually derives Genesis. So if I try to compile it now, it should complain that I'm not actually, yeah. Basically, it's saying that, hey, you gave me a new module, but you didn't really tell me how to, how to initialize it or how to do the Genesis, right? So it tells you exactly where you need to add it, which is pretty nice. So there is a Genesis config, and this is where when the rollup is starting, you're like configuring so all the modules that we defined in the code, all the other modules have Genesis. So we'll just end up adding the Genesis here as well. So for Genesis, it's basically, let me see. Yeah. And we just need to import that as well. So once it's imported, yeah, it says that, hey, I need this Genesis. So the simple token config should be part of this. And okay, I have a clone here, but I don't have a clone here. Yeah. So we'll just see if this checks. Okay, yeah. So at this point, we've basically completed our new coin module. So we can actually, let me just check if I missed something because UGB2 native, okay. Okay, implemented it, called it in. Okay, I think we're good because it's checking at this point. So one of the things we provide as part of Sovereign SDK is we containerize Celestia so that you don't need to connect to the network live if you're doing something. So we have a make file that is pretty comprehensive in terms of starting the Docker container and everything. So let me see if Docker is running. It drains battery, so I usually kill it. Okay, so I'm just doing make clean, which cleans up the Docker container. So at this point, if I start like a new, if I do make start, it starts Celestia locally for me. And yeah, it's just waiting for the container to start up. How are we on time? Okay, good on time. Yeah, perfect. So now the container is started and you can actually see Celestia actually generating these blocks, right? So now we start our rollup So just cargo run in demo rollup, and it should actually just start picking up blocks. Yeah, so whatever blocks are being generated by Celestia are being picked up here. The good thing is we just did a genesis, so we can check if our new token actually exists, right? Because in Genesis, we basically, let's look at what we said in Genesis. I said, okay, create a token with a supply of 1,000 using the sequencer address. I just used that because I didn't want to generate a new key. And if I do, like, this is just a curl command. It hits the RPC. And if you notice, the namespace and the function are basically what we specified in query. So in the query part, we said this is the namespace and this is the method, right? So that's basically what we're using here, simple token underscore get balance. And for the parameters, I'm passing in the address. So yeah, let me just see if this, yeah, so there's a token of balance 1,000 against this address. So now we can also try to do a simple transfer. So in order to do the transfer, what you need is, what is our call? We defined call, right? Let's look at call. So we need an enum of the type transfer with a to and an amount. So we automatically provide JSON SERD from your enum. So as long as you have a JSON that can be deserialized into this enum, you're good, which is basically what I ended up doing here. Let me quickly see where it is. Yeah. So in the requests, there is a simple transfer.json. And if you see, it's pretty identical in structure to the enum that we have. The transfer enum, I'm transferring it to a specific address, and I'll transfer like 100 tokens from, and so now I need to create the transaction, right? How do I do it? Yeah, so we have like the sovereign CLI, which handles a lot of these things. So I can quickly show you what it looks like. So if I do cargo run -h, it shows you the functions that are, by the way, let me know if any, you can see font is visible, right? Okay, yeah. So at this point, I can just, like there's a couple of, so this is evolving. We're trying to make it significantly easier as well. But once you have your JSON message, you want to serialize it to pass it to the server, right? So that's actually what we're doing here. So when I serialize, I tell it what the private key that it needs to use is. So the private key in this case is the sequencer private key. So let me see. So keys, and yeah, so it's this key. And then the module name. So that's also auto-generated, so we don't need to, the module name is basically simple token. That's what we generated just now. The call data is the JSON that I just created with the 100 tokens. So test data and yeah, requests, and you have the simple transfer.json, and then you need to provide the nonce. We didn't do any transactions from here, so the nonce is 0. So once I do this, it's essentially serialized this transaction. Celestia accepts blobs, right? So we need to bundle the transaction into a blob. By the way, I'm just doing all of this manually just to illustrate how it works, to give people an idea. It's much simpler. Like we already have something, like we already have a PR where the CLI gets the complete command line tooling for the module directly. So there's something like if you do sob CLI submit -h, now the module will turn up as an option. So yeah. So we serialize the call. Now we'll just bundle it into like, yeah. We have something called make blob, which bundles the transaction into a Celestia blob. You can bundle multiple transactions, but we only have one transaction here. So yeah, so there's like a simple transfer.dat, yeah. So it prints out hex, which is the API that Celestia accepts. I'll just put it into like a blob and submit it to the DA layer, right? We also have the RPC, there's also a sequencer module. So there's something called a publish batch and a submit call. So the sequencer does all of this. But just to illustrate it, I'm trying to run it manually. So yeah, so once we have a blob, in order to submit it, we just, let me see. make submit, and then okay, yeah. So it's make submit transaction, and all of this is in the documentation, so it's not test data. No, sorry. Yeah, so this is the blob, and we can see our rollup is running here, right? So it's still fetching blobs. I'll just submit this and see if it's, okay, it's submitted it, and we just have to wait for it to go through the Celestia and for the rollup to pick it up. Okay, yeah, so the sequencer outcome is like rewarded and it applied the state transition. So if we check the balance, I mean, we can check the balance of the new address, but we can just check the old one because that was 1,000 tokens. So now it should be, yeah, 900 tokens because 100 tokens have been transferred to the new address. Yeah, so that's like, how are we, 11, oh yeah, 12 minutes more. But yeah, that's basically what an end-to-end flow looks like. You define your module, and then you plug in your module into the rollup. That just requires like 2 lines of code, as you saw. There's an existing demo rollup, and you just, whatever Rust create native code that you created, as long as it satisfies the necessary traits, you just plug it in, and you write some logic for Genesis, and then you're good to go. And if you make any mistakes along this process, you get a compilation error, which is pretty nice. And yeah, so that's the demo part of it. And I think we have some time to go over like some internals of the Sovereign SDK as well, which is we have like the demo prover. It works in a very similar way to demo rollup, except that when it's running, it's picking blobs and also proving them. So we don't have enough time to like demo the prover itself, but it's completely compatible with the rollup. Like you get like if you put something into the rollup, you get the prover for free. So if a machine is running the prover, whatever is part of the rollup, it's all, like as long as you're able to generate valid RISC-V code, it ends up like generating proofs for it. And the prover is also capable, so your light clients can validate the proofs before accepting the blocks. So that's the prover part, and let me see. I'm seeing if there's, yeah. So regarding like work in progress, we have an EVM module that's already checked into main with the experimental feature, as I mentioned. The goal of the EVM module is, right now the example that I showed you is native Rust code for business logic, but this one would let you, this one encodes the entire EVM as a sovereign module, so you can actually deploy contracts and submit contracts and everything and interact with it as you would with a regular EVM rollup. Sorry, regular EVM chain. Our goal is to make it like fully compatible and RPC compatible with MetaMask as well. It's a work in progress, and I think it's pretty close, to be honest. And there's the OpenAPI spec generation as well. So these are 2 of the most immediate things we're working on, but we're also working on a lot of other stuff. Again, as I said, it's like fully open source, so anybody can, like, we absolutely welcome anyone to, visit, take a look. And we also, like, pride ourselves a good amount on like the documentation. So if there's anything wrong with the documents or anything, or if anything is not clear, you can always ask in Discord and we'll be more than happy to answer. So everything that I explained is a small part of the tutorial, and all of that is here actually. So when you get started, how do you run like a local DA instance, and what does the make file do? There are like, it's pretty comprehensive, and we want it to be, anybody, like we said, the goal for Sovereign is to let you focus on application logic. Like you shouldn't have to worry about anything to do with the prover, networking, storage, consensus, like just plug and play, start focusing on your business logic. So yeah, we have 10 minutes for like questions or, yeah? Anything? Yeah, go ahead.
First of all, great talk. Thank you.
Oh, thank you.
A few questions. I would say the first one is what consensus engineering, like what's the determined parallel you're using?
So because because it's a sovereign rollup, you don't really, the consensus is actually left to the base layer. What you care about is sequencing, because the ordering is done by the base layer. So we support Celestia and Avail right now, and like any DA layer that fits our adapter model can support it. So the consensus, like that's actually one of the beautiful things about rollups or sovereign rollups. You don't really need full BFT consensus in the application layer. The sequencing and the ordering and the reorg protection is actually from the base layer. So whatever Celestia uses, that's Tendermint. Avail might use something slightly different, but I think I don't know, Jim, do you know if the diagram is in the repo? I'm not sure if we put it there. Okay, yeah, that's fine. Yeah. So on the roll-up, what we care about in terms of protocol is decentralizing the sequencing. Yeah.
So you're not actually sending blocks, you're just sending the blob transaction.
Yes, the blobs.
Roll keeps they actually create blocks.
It's similar actually. So like you bundle your transactions into blobs. The blobs go into a Celestia namespace, and your roll-up full nodes, all of them. Let me actually see if I have the diagram. That would be cool if I did.
Yes, the concept of block is also virtual, and only the transaction data is sent to the base layer. And once the transaction data is processed, we virtually create like the block like state.
So when you handle the cache from the DA, it's like creating a virtual block concept.
A batch or multiple batches.
And the transaction from the DA is handled after it's proved only, so it needs to be both.
Um, Not depends on which node, because full nodes execute the transactions on their own, so they don't need to verify proofs. They can if they want to. But okay, you have your blobs going to the DA layer, right? You also have the proofs going to the DA layer. The full nodes are going to take the blobs from the namespace and directly execute the transactions on their own. The light nodes will wait for proofs. Because, so that way, I mean, full nodes don't really, so yeah. In terms of, for the user, if you're a light node, naturally you need to wait until it's proven. If you're a full node, it'll be bound completely by the DA layer. So as soon as the DA layer sequences the block, you're ready. You can apply state transition. I mean, there are optimistic models that you can use where you can actually take the blobs from the sequencer directly as well. And you know, if you have some assurance that they will be sequenced in a specific order, like degrees of finality, right? You can have like a soft finality where it's faster. So in the case of a centralized sequencer, you can directly take the blobs from the centralized sequencer because you know the order. In case of base sequencing, it's a little harder because the DA layer could reorganize it. If you have a more complex sequencing algorithm where they have a leader election process, that becomes slightly better. But you know, there can be a reorg if something happens and the algorithm isn't. Yeah. Okay. No, because you just keep posting blobs at network speed. The sequencer keeps posting. So the sequencer technically doesn't need to execute. It just needs to check. There are some validity checks that we actually do. So I don't think, so there's a sequencer logic here which handles the reward system. But to answer your question, the sequencer's job is not to execute. It's mainly to sequence blobs and post them to the DA layer. So you're only bound by the speed at the scalability of the DA layer and how many blobs it can accept. So you can keep submitting transactions, they keep going to the DA layer, and as long as you have a full node that is reading blocks as soon as they're sequenced, they're executed in order of what they're being sequenced as.
Only the full node.
The full nodes execute the raw logic. They don't need to care about proofs, but yeah. It is, yeah. Yeah, so that's actually another. You can completely customize logic module, yeah, it's basically currently what we have is so in the CLI I have an example actually. So let me quickly SDF src solve CLI cargo run. So there's actually two calls here. One that says submit call and publish batch. This is more like when you keep submitting it, the sequencer keeps holding them. When you trigger publish batch, it sends the blob. So this is in case you manually want to play with it, but you can tune it however you like. Like you can, like I said, the base sequencing model is more like as soon as you get the blob, you throw it into the DA layer. Yeah, there is some batching. By the default logic, we have it based on both time and number of transactions. Yeah. We're actually looking at IBC compatibility. Right now, bridging for sovereign rollups is more based on light clients because one of the reasons why for us actually provers are like first class citizens. Like we didn't want to go live saying we'll add this later. So if all the work we're doing with the prover system is completely concurrent to the full node and light node. So any other rollup that can run a light client can actually validate state on another rollup. So we're looking at IBC compatibility. Chem can probably talk a bit more about that.
Yes, we're talking with the problem and change log teams and what's happening basically. And there's the IBC and Rust module, like IBCRS. And we already have like demos of IBCRS being integrated as like a module that Rohan did today. Transaction from the IBC connected chain. And then for the other direction of going from sovereign SDK chain to a Cosmos chain, we're also going to build basically an IBC connection, but the right line will now be the regular connection to the data. SDK verifies that the data root and then like realize the state root of node. So we'll have an IBC connection.
Yeah, sorry, I'm just trying to find the diagram. Oh, yeah, here it is. We'll full screen it or, yeah, basically this is what the architecture would look like. You have, do I need to zoom in maybe a little bit? Yeah. So basically you have the DA layer, it's stuck for some reason. But yeah, you have the DA layer, you have the sequencer, the user submits the transaction to the sequencer, the blobs are posted to the DA layer, and they get sequenced in a specific namespace. And in terms of what is interacting with the DA layer, you have both the full node, the prover, and the light node. The full node's job is, let me just pick the blocks, let me extract the blobs that are relevant to my namespace, I will validate them, I will execute them, and I will modify the state. The prover, on the other hand, is like a superset of the full node. In addition to executing it, it also creates completeness and correctness proofs for each of the blobs, generates the proofs, and those proofs get posted back to the DA layer. So what you have here is the light nodes, on the other hand, they sync only the headers of the DA chain, and they sync the proofs from a different namespace. So this is basically what the very raw, minimal architecture looks like. Oh, that is completely, that's basically what the rollup was doing here when I ran it, which is, yeah, this is typically what you would actually do is every DA layer also has a light client, right? because the light client already syncs the headers and fetches the data. So you would actually use the logic of the light client to do that. You can write custom logic and interact with the API as well, but the good thing is most DA layers come with light clients and nodes that also do some validation for you, right? Because you don't you can fetch a block, but now you need to validate whether the block is correct or not. It's better to leave that to the DA layer. So. Yeah.
Is the full node architecture design right now such that all historical state things are recorded in some database or with some sequence index design?
So we actually use, the default implementation uses JMP, like the jellyfish Merkle tree, because it's easier to prove. I'm not sure I understood your question about indexing, but yeah, currently there is no state pruning, if that's what you're asking, but we have discussed on like state expiration or something to prevent like state bloat. But yeah, like the full node implementation is basically that as you keep getting blocks, you keep building your JMT and it keeps growing. Yeah.
Well, I guess all historical state and state changes would be on the DA layer.
The blocks would, so when you say state, there are two things, right? There is the actual state tree, there is the ledger. So the ledger can be pruned very easily because you only might need to maintain the last 1,000 blocks or last 2 or 3 epochs or something. But your, the state tree itself is maintained in full. But also one of the reasons why we went with RISC-0 initially is there's recursive proofs. So we're looking at a model where in your ledger, as you add new blocks, you recursively prove so that at any point in time, you can sync the entire state tree and know what the Merkle root of that is, and there is a proof of that as well.
So in order to get the state of your rollup 1 year ago, you have to sort of
you have to reread it from the, there are, like I said, it's recursive proofs, but the intermediate proofs are also submitted on chain. So 2 options, right? One is if you want, let's look at it in terms of blocks. If you want this, like let's say currently we're at block 10,000 and you want the state at block 4,000. One option is you play from Genesis. The other option is if you have snapshots, because we have recursive proofs, if somebody says the state at block 800 is X, and this is the proof for that, if you can just download the state snapshot, you already have proof that that's the correct state, because the proof is also published on the chain. And you only need to play the remaining 200 blocks to get from block 800 to block 1000. Yeah. So that's actually one reason why we're very interested in recursive proofs. Sorry, yeah, I think, okay, yeah, we're already 5 minutes above, but we'll be around for questions, so.
And we'll definitely